Thank you very much, everybody. Thank you for coming. It's quite an audience for this kind of talk, so I'm very happy to see all of you. I gave this talk a very long and tedious title, but actually Rigor in Society and Mathematics is just as good. What I'm going to talk about is standards of rigor in various sorts of historical mathematical cultures, and how they depend on the specific contexts of those specific societies. So how rigor is not some abstract ideal that is just out there and mathematics tries to capture it gradually, but rather is something that is created and adapted to very specific social settings. Let's just jump into it and start when one often starts when talking about mathematics, that is classical Greek mathematics. Not because it was the first mathematical culture, there was a lot of mathematics before that, and you heard, I think a couple of weeks ago, about Egyptian mathematics, but it's a heavily researched one, so we can say a lot about Greek mathematics. And I want to start with a social context. I want to start with explaining to you who these people who did mathematics, this kind of, let's say, Euclidean mathematics, Euclidean geometry, the kind of mathematics associated with Euclid and Archimedes in ancient Greece, who were they and what were they trying to do? And I'm going to be very simplistic because I can't take too much time, so I'm going to be very sketchy and overgeneralize, but still, the broad picture is that classical Greek geometry was a minority enterprise. We're talking about very few people. It was an elite enterprise. So the people who were doing this kind of Euclidean geometry usually belonged to the social elites. And this was an enterprise of distinction. This was about being different, doing something special than what other people around them did. And to highlight that, or to their goal in that was to create a mathematical culture that is, by achieving consensus, shows itself to be, or at least pretends or claims to be, about something higher, about some sort of super worldly truth. And I'm going to follow here the narrative of Revier Netz and Marcus Asper, of course, building on many of their predecessors. So the characterization is going to be something like, first of all, these kind of mathematicians, the one associated again with people like Euclid and Archimedes, were aiming to create a kind of mathematics that was distinct, that was different from the mathematics of those who did mathematics for a living, who were paid for doing mathematics or were enslaved for doing mathematics, such as land surveyors and accountants. And this implied various things, or this was achieved by various means. For example, there is a strict separation of geometric magnitudes from numbers in the classical Greek geometry. So if you're a land surveyor or an accountant, you have to measure things by number. But these kind of mathematicians completely separated the geometry from the numbers. You never see in Euclid the length of this line is 2, or the area of this triangle is 4. It just doesn't exist. There's a deliberate and strict separation to differentiate themselves from those who measure things for a living. Practitioners need calculation algorithms and calculation methods. These kind of classical geometers were really trying to get away from this and not to discuss that. Instead, when they were discussing number, they were discussing properties like primality or even an odd, not how to calculate. This kind of classical Greek mathematics depended on counterfactual definitions and axioms. So definitions and axioms that do not really reflect what's going on in the real world. For example, when you say that a point has no part, or that a line is a length without a breadth, or that given a line segment you can always continue it, these are not things that make sense from a practical point of view. You draw a line, it always has some breadth, you have a line segment and you try to extend it, eventually I'm going to hit the wall. But by making this idealized counterfactual assumptions, they are again separating themselves from the practical mathematicians. And one of the most important features, or at least the most celebrated features, is that they focus on reason rather than use. It's not about making useful results. The useful results were already there. It's about explaining, reasoning, justifying, so a different kind of focus. But it's not just about distinguishing themselves from the lowly practitioners, the land surveyors, the accountants, whatever, but also from the more elitist kind of debate that in these contexts, if we're talking about the Greek polis, paradigmatically Athens, which happened around politics and law. So political decisions are made in assembly by speeches, legal cases are decided by jury, and there's a lot of rhetoric involved. And around this, there's a culture of being able to convince, the sophist culture or the rhetorical culture of learning how to convince. And the mark of a good sophist was to convince of anything. You give me this goal, I will come up with a way to convince of that. You give me the opposite goal, I'll come with a way to convince of that, like in a debate club. And these kind of people doing this classical Greek mathematics want to separate themselves from these people as well. They want to create a system of argument where you cannot argue for everything, that you have to agree, that you generate an agreement about what is the right conclusion or the right result. And there are various ways they achieve that. So for example, they have a very rigid formulaic language applied to qualitative diagrams. By formulaic language, I don't mean formulas, symbolic formulas in the modern sense. I mean a very restricted language with a very small vocabulary and very rigid structure, compositional structure, syntax, sorry, that really limits what you can say and what conclusions you can justify. And it's all connected to a qualitative diagram, so a diagram where you don't really care about the scale, you just care about the let's say topological relationships or qualitative relationships. So by embedding the discussion in this kind of ground, they create more consensus. Again, the counterfactual definitions and axioms also play a role in creating consensus because they simplify things and limit the range of possibilities that might interrupt reasoning in a real life setting. And this meant that they reached a very high level of consensus around the core of geometry. So they did manage to get what they want. They did manage to create a kind of knowledge, a kind of science that was separate from the practitioners, deliberately separate from the practitioners, but also very consensual and not open to anything goes, as in the political and legal debate culture of the time. However, this consensus was not absolute. There is a consensual core in classical Greek mathematics, but there's also a lot of room for debate, much more than we tend to acknowledge today. And this was important. This was important because this was again, a minority enterprise. There are few people. There are no stable institutions for this kind of mathematics. And that means that it's very difficult to build knowledge higher up. It's very difficult to introduce new mathematical structure building on previous mathematical structures because there's not enough of a stable audience that can keep up. So effectively, by the time of Archimedes and Apollonius, the classical Greek mathematical universe is saturated. This is 3rd century before Christ. So you cannot distinguish yourself as a mathematician by building up new mathematical objects. Instead, you need to distinguish yourself either by making variations on what others did, or better yet, distinguish yourself from your predecessors and your colleagues by arguing better. So showing that their argument were not good enough, were not careful enough, were not sound enough, and you are doing better. So in order to create this space of debate, there had to be room for disagreement. You had to find ways to find fault with what your predecessors or colleagues did. So it's a very interesting balance between a consensual core and a consensual discourse that says, look, we all agree, therefore we are right about something, and if something is not plain reality, but some sort of a world where points have no parts and lines have no breadth. But also, there has to be room for debate so people can distinguish themselves. It cannot be too consensual. So this is the big picture, and now I'm going to spell it out in an example. Well, what does it look when you actually do mathematics? So I'm going to Euclid's Elements, a proposition that I guess you all know from school. In any triangle, if one of the sides is produced, that is extended, the exterior angle is greater than either of the interior and opposite angles. So here the triangle is ABC, and the exterior angle ACD is going to be larger than the interior angle B, also from A, but we will focus on B. So how do you prove such a thing? You prove such a thing by applying your very restricted language of argumentation to this diagram, and you say in these very specific idioms with its very specific grammatical and rules, you say something like the following. You take the line from B to the middle of AC, you extend it. Do you see my cursor? Oh, you don't see my cursor. Let's see. Here. Okay, and yeah. So you take the line from B to the middle of AC, you extend it in the same direction, you reach the point F, you connect it in a straight line to C, and then you can show, according to this, the rules of this very restricted kind of argumentation and the previous results, that this angle FCD is going to be equal to the angle ABC, and since FCD is inside the external angle and it is equal to the angle B, the external angle is greater than the internal angle. So everything is very rigorous, very rigid, following all the rules of the game and the specific language. However, there are some things that the specific language definitions, the axioms, the rules of argument do not give you. And that's, for example, excluding the following situation. Excluding the situation where when you continue from B to E and when you go from B through E in a straight line in the same direction, when you reach the point F and connect it to C, you are no longer in this angle. Sounds very weird. I had to draw it very weirdly. I mean, this is clearly doesn't look like a straight line. But the point is that this weird situation is not excluded. There's no argument that shows you that this weird situation does not happen here. There's no definition that shows you that it doesn't happen. There's no axiom that shows you that tells you that it doesn't happen. There's no previous theorem that says it. You just assume that this is the case. You assume that this is the case more or less by looking at the diagram and seeing that this is the case. But something here is excluded without any explicit ground. And this is more of a problem than it might seem, at least from a modern point of view. So I'm going to open a bracket for those who know a little more about geometry, about non-Euclidean geometry, but in 2 minutes I will get back to the part that I hope everybody can follow. So this aside, for those who know, this theorem about the exterior and internal angle, it doesn't work in elliptic geometry. This weird situation that I drew could happen in elliptic geometry. And surprisingly, and less well known, is the fact that under a reasonable interpretation, elliptic geometry fulfills all of Euclid's basic assumptions. Euclid's explicit statement do not exclude elliptic geometry. Under a reasonable interpretation, there is some gray area there. Which means that at least under this reasonable interpretation, you cannot prove elements 116 based on Euclid's explicit assumptions and definition. It's simply impossible from a modern point of view, at least. So in order for this to work, you have to make some sort of implicit assumptions. And there are many known implicit assumptions in Euclidean geometry about betweenness, what is between what, superpositions, what you see without an explicit verbal justification. And in this case, indeed, what's happening here is that certain implicit assumption about where things lie, what lies between what, would exclude this situation. So you have to rely about things that are not said explicitly. Now, it's a problem because if things are used and are not said explicitly, it often can create ambiguities. So if Euclid does not specify the exact nature and scope of his explicit assumptions, he only uses them in specific cases, then it's up to the reader or interpreter to figure out what is the general scope of these very specific inferences. How do you generalize them? What is the intended generalization or correct generalization of these strange steps that just happen in the middle of a proof without any explicit grounding? And this means that the reconstruction of the generality or scope of implicit assumption has to be justified by geometers not based on the explicit statements, but rather by figuring out what geometry is really about. So part of what justifies classical Greek geometry is not the definitions of axiom, but understanding what it is really about. And to explain how it works using what your understanding of what mathematics is really about, I'm going to look at a proof by a later Arabic mathematician who was working in this tradition, who gives you an example of how you establish an assumption that you are going to later use, which is not based on anything explicitly stated in the axioms or definitions. So this is Ibn al-Haytham, 10th, 11th century mathematician, and he's proving the parallel postulate, which already might sound very strange to many of you, because from the modern point of view, you cannot prove the parallel postulate. You cannot prove the axioms relating to parallel lines in Euclidean geometry from all the other assumptions, from all the other axioms and definitions. From a modern point of view, it's simply impossible. However, Ibn al-Haytham thinks he can, and he explains to you what needs to happen in order for his proof to work. So he says, consider a first given straight line segment. So this is going to be my arm here. And we further imagine a second bounded straight line that forms a right angle with the first. So this is my second arm here. We further imagine this second perpendicular line to be moving with one of its ends, this is my elbow, with one of its ends along the first straight line in one direction. So one line moves on the other in one direction. During the time when it is in motion, the other end of that perpendicular line, my fingertips, will describe a third straight line. So if I'm moving this line, keeping my elbow at 90 degrees, then my fingertips will draw a straight line. And one can imagine this line, and as well as this kind of motion. And this is actually enough to prove the parallel postulate. This seems completely harmless, visually very obvious, but it's precisely the kind of things that are so subtle about Euclidean geometry and that are not captured by the explicit assumption. Did Euclid intend or not intend for this to be assumable? Should it be assumed or not? This is precisely the gray area I'm talking about. And look how Ibn al-Haytham justifies it. He's not the one and not the only to, is not the first and not the only to make such arguments. This is, there are many arguments around this family of arguments from antiquity to early modernity, or actually later than that even. But look how he justifies it. He says, imagine. And by imagine, he doesn't mean imagine in some everyday sense. He's committed to following Aristotelian philosophy. So imagination in Aristotle means something very specific, and he's following the assumption about this kind of understanding of the imagination. And in this kind of understanding of the imagination, this should be permissible, at least according to Ibn al-Haytham. But of course, others might understand mathematics as being about something else than the Aristotelian imagination, or maybe they might understand the Aristotelian imagination in different ways, and then they might disagree. And again, brackets, I'm opening brackets for those who know a little more. This approach means that everything we know from non-standard model or non-Euclidean models is completely irrelevant. Because when you look at the non-standard model, what you call straight lines do not look straight. Imagine all of those models of hyperbolic geometry, for example. You call it straight line, but it's not straight. And because it does not look straight, this is not what geometry is about. And therefore, all these kind of models, even if you show them to a classical geometer at the time, he would say this is completely irrelevant. So again, a very different standard about what may or may not be relevant for arguing in Euclidean geometry. Closing the bracket, going back to our main discussion. Because geometry is about something that is not reducible to explicit axioms and definitions, and it doesn't matter if this something is the Aristotelian imagination or some other epistemology or ontology of mathematics among the many that have been developed through the centuries. And seeing this something, again, Aristotelian imagination or something else, is somewhat ambiguous, geometers did not always reach a consensus regarding which geometrical arguments are valid. And this is the situation of the tradition of classical Greek mathematics. A lot of disagreements about what does or does not work. And this goes very late. I'm not going to read this quotation by Montucla, but just notice the year 1799, how late people still describe this situation in rather ambiguous terms. So I think that the general characterization would be something like everybody believed that what Ibn al-Haytham tried to prove, the axioms about parallel lines from the elements, are true. And I think more or less everyone, at least until the 18th century, believed that there are correct arguments or proofs, but they didn't agree which one were the correct proofs. So this, I'm telling this story in order to try to give you the idea of how classical Greek geometry and how we understand geometry today work very differently in terms of the rules of the game. So if in modern geometry it's all grounded in explicit assumptions, axioms, definitions, rule of inference, whatever, classical Euclidean geometry or classical Greek geometry, it should be here, is grounded not only in that, it's also grounded in some ambiguous ontological, epistemological ground, what mathematics is really about. In the case we saw, the imagination, what we can imagine correctly. And this means that in modern mathematics, because we follow this system of explicit assumptions, and only that, it means that we can attain consensus about the validity of arguments. Now this is a bit of a caricature of mathematics, but I'll get back to it at the end. However, in the classical situation, the fact that mathematics was not only grounded in the explicit assumption meant that disagreement about the validity of arguments was possible and alive and part of the story. For example, when talking about trying to prove the parallel postulate, trying to prove the axioms about parallel lines from the other axioms. In modern geometry, this is clearly impossible, and we use tools like non-standard models to show that. In classical geometry, well, it was possible, it just depended on how you interpret what geometry was about, and what geometry was about had nothing to do with non-standard model. It was about what looks like the right geometry, in a sense, or at least according to some, let's say. Okay, so this is a story I want to tell about Greek mathematics, and in this story, the disagreement, the lack of consensus, was not a bug, it was not a problem, it was a feature. So it was important for this whole enterprise to reach high levels of consensus to distinguish itself. But it was also important to open up a realm of discussion, because otherwise, given that it was such a small and distributed enterprise, it would simply die out without having anything to argue about and without having the critical mass to build up. This whole thing would simply die out and mathematics would have become fossilized. Okay, so this is the classical Greek tradition, but this was one very specific mathematical culture, and there were many, many others across the world. And in most mathematical cultures around the world, mathematics wasn't that special. It didn't have this elevated status that we associated with it with today. In the other well-researched mathematical cultures like ancient Iraq, what we call Mesopotamia, or ancient Egypt, which Annette here talked about a couple of weeks ago, also within the Greco-Latin world, or in China or India or in the Islamic world, usually mathematics did not have an exceptional status compared with other forms of knowledge. It was not necessarily considered the purest, the best, the most rigorous, the most secure kind of knowledge. It was more or less one among many other kinds of knowledge, except if you look at those people who actually follow the classical Greek mathematics. So this is kind of the legacy of this specific mathematical culture, which singles out or tries to single out a certain way of doing mathematics as something special. And there are many examples. I'm going to discuss two of them. One is going to be the context of canonical Chinese mathematics. But before I say anything about Chinese mathematics, I need to give a disclaimer. So if you hear anyone saying something like Chinese mathematics was so-and-so, or Indian mathematics was so-and-so, 99 out of 100 cases they will simply be wrong. Because these kind of cultures are too broad to be generalized over. We're talking about hundreds, sometimes thousands of years. We are talking about huge geographical areas, multilingual areas, with various different groups doing mathematics in various different ways. Just like in Greece, you have this elite Euclidean geometry, but also the practical geometry of the surveyors. It's very difficult to generalize over that. So what we have is a huge amount of mathematical work, or maybe not huge, but a lot of mathematical work. And then from that, a certain small subset actually survives and reaches us. And from that, only a small subset is actually research. And from that, one can maybe select a small corpus on which one can generalize. So everything I'm going to say now about Chinese mathematics is actually about a very specific subset of Chinese mathematics. So I'm going to talk about the canonical Chinese mathematics that was developed in the context of the imperial bureaucracy as part of a rather integrated system of knowledge, which was on and off going on around the first millennium in a rather unstable manner. The social context of this mathematical production was the centralized imperial administration. So these are things that are usually done around the imperial bureaucracy, the state bureaucracy. And usually in a centralized education context under Confucian ideologies, which were usually more or less, again, difficult to generalize, state ideologies. Now, if you look at this culture of canonical Chinese mathematics, then you can find, when you look at how they solve problem, you can make several points. And here I'm following the work of Karine Chemla. So the general structure is presentation of procedure for solving paradigmatic problems. You have a kind of problem, you want to find a solution, but unlike what you might find being said in many contexts, this was not just a recipe mathematical culture, not just mindless list of methods. They were really interested in justification, and you find the justifications both implicitly and explicitly when they explain how to solve problems. But it's not only about justifying in the sense that we expect, it is also about systematizing the mathematical knowledge by finding cross-cutting principles that are spread out around mathematics, and not only that, but also embed them in a broader philosophical context. So to justify something mathematically is not simply to find a step of reasoning that leads from assumptions to conclusion. It's about systematizing, finding echoes between different aspects of mathematics and echoes between that and philosophy. And let me give you a small example. I'm talking about addition of fractions. Obviously, this is not a Chinese notation, but we'll have to simplify. The method of solution is what you would expect. You take the denominators, you make a common denominator. Because you made a common denominator, you have to compensate the numerators. So that's the rule. The commentator, in this case Louis, is explaining how and why it works. But then he also says something funny. He says he calls this operation of taking the common denominator equalization, and then the operation of correcting the numerator to reflect the common denominator homogenization. And it's not clear when you look at it first why he introduces these names in the middle of the explanation, but then if you look outside, you see that these terms appear elsewhere. For example, when solving a system of linear equations, again, not original notation, but close enough for us. When you solve a system of linear equations like these, the first thing you do is equalize the coefficient of x, multiply here by c, multiply here by a to get the same coefficients, and then homogenize, multiplying the rest of the coefficients by the corresponding quantities, corresponding factors. And then once these coefficients are the same, you can subtract. I keep pointing and you don't see where I'm pointing, I'm sorry. Once you have homogenized, equalized the coefficients, you can subtract the second equation from the first, and the x will disappear. You can solve for y, and then you can solve for x. So basically what we learned at school. But instead of looking at this as two separate problems, they are being related by a sort of common mathematical principle that organizes them. And importantly, this is not just a mathematical principle, it echoes terminology and principle in the philosophical system in which this is embedded. So the whole system of change and balance around which this kind of Chinese cosmology is organized is reflected by these terms and operations of equalization and homogenization. So to prove something, to understand something, to establish something mathematically is to embed it in this broader context of principles. Something very different than what we expect from today, or what we know from Greek mathematics, or maybe not so different depending on how you look at it. Let me give you another example, again from a culture that's not from a context where things are done a little differently. This is the social context of European mixed mathematics. Mixed because they mixed the principle of pure mathematics with things that happen in the real physical universe. So mixed mathematics, something that was very popular in Europe from early modernity to the 19th century, maybe going back before, but we are focusing here on that. This kind of mathematics grounded the understanding of both natural and social orders in practices of quantification and accounting. So just like you quantify and balance an account book, you quantify and balance the physical universe or the social circumstances that you're trying to understand. Again, I'm going to describe first the social context and then give you an example. So we are talking about a kind of mathematics, a way of doing mathematics that emerges or at least becomes very popular with the rise of the new classes of early modernity, the artisanal, the merchant bourgeoisie. These are new groups who gain dominance in society, and as they gain dominance in society, they want to be associated with a distinct kind of knowledge. They don't want to replicate or simply continue the classical past knowledge associated with old authorities like the church. They want to have their own language of knowledge. And some of the characteristics of this new way of doing mathematics is that the classical geometrical standard, the Euclidean standards as transmitted through Greek, Arabic and Latin traditions are no longer considered as what guarantees a higher truth. Many of them are rejected, many of them are amended, many of them are thought to be insufficient or too harsh. This is no longer what guides mathematics. They allow themselves to mix the tradition of the classical Greek geometry as transmitted with other traditions, practical mathematical traditions of coming from the world of artisans and merchants. And in doing that, they incorporate directly and indirectly Arabic and other Eastern mathematical knowledge. So it's a real hodgepodge and amalgam of approaches to mathematics. But altogether, there's a culture where nature is viewed as mathematical. So the cliche example is Galileo's quote about the universe written in is a book written in the language of mathematics, but it was a rather widespread view. So you understand the universe or even society in many cases by quantifying and finding what balances what. You balance equations like you kind of balance the books. Now, what does it mean for mathematical standards or for concepts of proof or truth or rigor in mathematics? So I'm going to give one example, a reconstruction of Euler's mathematical methodology. Euler is the mathematician of the 18th century. His influence on what mathematics was and became was immeasurable. And according to a reconstruction by Ferraro, the way he thought was that the way he was thinking about mathematics was that a mathematical theory was acceptable only if it conformed to their reality. Now, this is a difficult thing to explain because there's a lot of mathematics that doesn't seem to conform to reality. Zero, negative numbers, complex numbers, infinitesimal, they're all very murky and difficult to associate with reality. So I'm not going to explain what it means to conform to reality, but everything has to be somehow directly or indirectly associated with reality. And since reality is unique, alternative theories based on alternative definitions of certain notions could not exist. Since you have one reality and mathematics is grounded in reality, there can only be one mathematics. You cannot have, like today, different Euclidean and non-Euclidean geometries. Everything has to be embedded in the one reality. And this gives rise to things that would be very suspicious from our point of view, from a modern point of view. So, for example, when Euler decides to calculate the value of this series. So the series is 0 factorial is 1 factorial plus 2 factorial is 3 factorial, etc. Or if we spell it out, 1 minus 1 plus 2 minus 6 plus 24 minus 120 plus 720, etc., etc. Now, obviously, this is a divergent series. This does not converge. There's no value to which this sum approaches. These are ever-increasing negative and positive numbers. It just goes to infinity both ways. It does not converge. And there was no question about Euler understanding that it does not converge. Euler understood convergence and divergence much better than anybody in this room because he calculated by hand. He he understood convergence and rate of convergence and asymptotic convergence perfectly. However, even though this does not converge, Euler was convinced that being a mathematical expression and since mathematical expressions are grounded in reality, it should have a value. You should be able to calculate the value of this sum, even if this value is not what this sum approaches. It's not the limit in a modern terminology. So what did he do? Well, he took all sorts of tricks and methods which he and others had used to calculate all sorts of series. And he used one trick and did all sorts of calculation and got one result. And then he used a different trick, taking a different direction and calculated, and he got the same result. And then he took a really crazy, completely different approach, building up on very advanced stuff, and he still gets this 0.59 something. So it's 5 or 6 methods, and he keeps getting the same result. And this is for him convincing. That's when he says that, yeah, okay, this has to be the right value. Not because every step in every method is safe, because he was very well aware that not all these methods and not all these steps were always safe. They could lead to contradiction if handled without care. But if all of these reach the same thing and you assume that it is grounded in reality, then this has to be the right value. This is how Euler, or someone like Euler, thinks about these things. So having seen these very different approaches to what it means to prove or to establish mathematical knowledge, let's go to what's going on today, modern research mathematics or modern academic mathematics. And the story we usually tell about mathematics is that mathematics is done in a formal, logical language with explicit mathematical definitions and axioms and rules of inference. And moreover, that all the inferences must not only follow explicit rules, but these explicit rules have to be mechanically verifiable. We have to be able to perform them not only by understanding human, but also by machines that follow algorithms. If everything follows this kind of formal logical structure, then the mathematical result is right. This is how we often tell what mathematics is today, from axioms through rules to results. Of course, that's not really how mathematicians do mathematics. If mathematicians really broke everything down to these very basic and tedious formal languages and rules, nothing will move. However, this formalization do have a role in fine-tuning mathematical arguments and making things precise and solving all sorts of disagreements and conflicts between mathematicians. So even though we don't really do mathematics formally, formalization as something that grounds mathematics has a role in keeping mathematics together and consensus today. And this kind of consensus is very impressive. Mathematics is more consensual today than it ever was in history, let's say up to beginning of 20th century. So past mathematical culture were much more agonistic, argumentative about disagreements than what we associate with mathematics today. And also this consensus is much stronger than what you see in other sciences, other contemporary sciences. Mathematicians tend to agree at least about the validity of arguments. They disagree about many other things, but about the validity of arguments they agree more than other scientists in other domains. And you might say, great, this means that our mathematics is the best or better or achieve what it needs to achieve, because we have various virtues associated or achieved by modern mathematics. We have consensus, the ability to agree about what is the right argument. We have autonomy, because mathematics is grounded in these explicit rules. It doesn't have to depend on our imagination or philosophical principles or reality. It really is autonomous. It can be expandable. You can always create new mathematical structures with new rules. So a lot of great virtues coming with this formalization. However, not everybody, if you look among the leading mathematicians, not everybody was very happy with this kind of way of doing mathematics. And you have some big names that come up objecting to some of the more formal ways of doing mathematics. I'm not going to explain who they are, it doesn't matter for us. And the objection had to do with some vices of the kind of mathematics that is formally grounded that we use today. If you just follow formal rules, formal definitions and axioms, you come up with all sorts of weird artifacts, with kind of pathologies, monsters that for many mathematicians are more distracting than useful. They distract you from following what is really important. This kind of formalization may be seen as detaching mathematics from application or motivation, because it's all grounded in these formal rules and not in what you want to do with it or why you wanted to do mathematics. Again, associated with loss of intuition or meaning, because following formal rules, following the letter of the law, sometimes does not really make sense. You don't really understand what you're doing. You know that it works, but why? It's a bit murky. And it can lead to fragmentation. One domain of mathematics has these rules, the other domain of mathematics has those rules. Communication is not great between them. They don't necessarily understand each other. So there are some problems, some legitimate critiques of problems that may arise from this way of doing mathematics. So if this way of doing mathematics, grounding mathematics formally, emphasizing consensus and autonomy and expandability, is not the only way historically to do mathematics, and even by people who were around when it was happening, was not seen as necessarily the best way to do mathematics, then we have to explain why mathematics came to be associated with these things, with formalization, with these values today, whereas it was very different in the past. And again, I'm going to try to offer a social explanation. And I'm going to look at one of the places where this kind of mathematics, this kind of mathematics emerged. So the 19th century emergence of a new kind of pure mathematics, a kind of pure mathematics that did not really exist before in 19th century Prussia. Not because this was the only place where this emerged, but this was one of the most interesting stories, and I think one that we can tell with a good level of understanding. And I'm following the narrative of a historian called Gerd Schubring, and it goes more or less like this. The starting point is neo-humanism, which was a sort of ideology. It was popular in Prussia at right after the beginning of the 19th century, some sort of reaction to the Napoleonic Wars, in a sense. Prussian neo-humanism was a worldview that emphasized the Bildung, the formation of virtuous citizens by developing their cultural, their moral, and their intellectual faculties. You have to create good citizens to have a good state. And the way they saw fit to develop the cultural, moral, and intellectual faculties of the citizens was through, first, classical languages, Greek and Latin, second, history, and third, surprisingly or not, mathematics. Mathematics was supposed to be sort of something that helps you develop intellectually. This kind of ideology focused not on the divine aspect of knowledge, but on the human aspect of knowledge, and therefore eroded the authority of religion or the church over knowledge. It had some economic aspect, like in the economic realm, neo-humanism emphasized creativity and self-initiative. You had to create something new if you were a good citizen. But whatever you create or develop under this ideology, it's not reducible to the utilitarian focus of Enlightenment or maybe French Enlightenment. So it's not only about making practically useful thing. It's really about also developing cultural and personal virtues. Now, this is not only an ideology of the times, it's not only something that some big thinkers preach for, this is also a state intervention. So there is an educational reform at the time being based on these kind of ideas associated with von Humboldt famously, but not only him, obviously. And when this educational reform based on these principles is implemented, you get various results. First, you need many math teachers for school. If the education reform emphasizes mathematical teaching, you need mathematical teachers. Now, since teachers under this reform are no longer trained in the theology faculty, because we don't want a theological authority over knowledge, they don't want, the teacher training moves to the philosophy faculty, where mathematics becomes an autonomous subject. And in the philosophy faculty, they need to find ways to teach their students, and their main inspiration, or for many of them, or for some of their leaders, the main inspiration is the philology seminar. So the development of philology in the 19th century, comparative linguistics, analysis of formal relations between signs, critique of sources, very careful conceptual analysis, hermeneutics. This is all the kind of knowledge and environment which mathematicians look at and say, okay, let's try to teach our students like that by really analyzing meanings and following formal relations. The focus is not utilitarian. It doesn't have to be about describing the universe. It doesn't have to be about physics or hydrodynamics. Anything that develops intellectual faculties can be part of that. And there's a research imperative. The self-initiative embedded in new humanism means that the new teachers are not going to be just teachers. It's not enough to profess your knowledge. You have to be a creative research mathematician in order to be a teacher in this, according to this ideology. So there's really a lot of mathematical production. Now, what does this all mean? If you take the fact that there's a large demand for school mathematics teachers, and the fact that these teachers are trained in the philosophy faculty, in this autonomous discipline that mathematics becomes, you get a critical mass of mathematics students and researchers in universities. And this is new. You may what I said at the beginning, that Greek mathematics was a minority enterprise. Mathematics was a minority enterprise for a large part of its history, and suddenly you have a critical mass. The other thing is that all these characteristics of new humanism encourage the creation of new mathematical languages. They encourage the creation of conceptual and formal mathematical languages because they are inspired by the philology seminar and formal relations and conceptual analysis. It emphasizes didactics because these are teachers being trained. And because of the non-utilitarian focus, it can be autonomous. It doesn't have to depend on physics, on engineering, or even statistics. And since there is an imperative to create something new, they create new ways of doing mathematics, new mathematical languages to express old and new mathematical structures, objects, achievements. This is the new pure mathematics that emerges in Prussia at the time. And it emerges from a very specific social situation. Now, the impact of that, having a critical mass engaged in this creative endeavor of new mathematical languages, is that mathematics becomes more and more autonomous. Because mathematics develops new mathematical languages which people outside mathematics no longer understand and therefore cannot control mathematics. Mathematics becomes self-controlling because it is less accessible to people outside it. It becomes more conceptual because of the more consensual because of the focus on the formal and conceptual analysis. It's really about clarifying things very clearly. And it is expanding. You can create new mathematical languages in which to try to do mathematics. And some of this is a feedback loop. Some of it is a self-sustaining structure. The fact that mathematics is autonomous means that it can continue doing what it does, creating these new mathematical languages. The fact that it is consensual across this large mass of different universities with many students in each university means that it can hold together as a professional discipline. So there's a kind of a self-sustaining environment of creating this new kind of mathematics. But, and this is going to be the end of the story, there's a twist plot. There's a twist in the plot. Neo-humanism is an ideology that works for a while and, like most ideologies, goes away. It takes a few decades and let's say the main ideology in Prussia, or now it's Germany more widely, is more of a technological utilitarian ideology. People don't care as much about these old neo-humanist reforms and rhetoric. But by that time, this new kind of mathematics already exists. And now the question is, will it survive? Given that the impetus, the motivation is gone, will the new achievement, the new pure mathematics, will it survive or not? And then mathematicians need to figure out what can help us survive. And they look at what they have achieved. And they have achieved an amazing, if not actual, at least potential consensus among mathematicians about what is or isn't valid in mathematics. This becomes the distinctive achievement of mathematics. They achieved an exceptional consensus. And this consensus is impressive. Other scientists look and say, we never managed to achieve this much consensus. Probably they get something right because they all agree with each other. And this becomes the identifying feature of mathematics and its raison d'etre, its self-justification. Consensus is not just an effect of a certain way of doing mathematics, it also becomes now something that justifies mathematics and therefore becomes a real goal of mathematics in itself. And that's what happens at the turn of the 20th century. This big movement of formalizing mathematics, grounding mathematics in formalization in order to maintain and increase the consensus that has become the self-justification of mathematics. And this is why today, when we talk about mathematics, we immediately associate it with consensus, with the one right answer, with the absolute knowledge. But this is a kind of epiphenomenon. This is an effect of a certain history, a certain trajectory, or rather short-term trajectory of ways of doing mathematics in specific institutions. If you look back, mathematics across history was not necessarily exceptionally consensual. There was a certain level of exceptional consensus around classical Greek mathematics, but if you look outside it, you don't see that anymore. So what I'm trying to say here is that different kinds of rigor are associated with different conditions, different social conditions, different motivations, different situations in which different kinds of mathematics develop. And whether our mathematics, the way we do mathematics, is still right for us, or should be right for the future, or should be changed with changing circumstances, is something that we will have to wait and see. And that's all. Thank you very much.